Okay, so this video is basically an instructional video for the three-dimensional static strength prediction program software that you'll be using in your Ergonomics 224 class. So the first thing that we're going to want to do is we're going to have to find where 3D static is located on your computer. And if you go to your programs, it is under the University of Michigan, who developed the software, and under the icon 3DSSPP. It's going to bring up some disclaimers. You're just going to say OK, and you'll get a window that looks like so. And so now you should have 3D static opened up, and you'll have 4 different views. You'll have the top left is the view from atop. The middle view up here is the view from the frontal axes, or plane I should say, pardon me, and then the top right-hand corner is the sagittal plane, side view. The 3 windows up top allow you to manipulate the mannequin, which will then be represented down here by the 3-dimensional mannequin, such that if you make any changes in these top 3, it'll be reflected down here in this 3-dimensional mannequin. The first thing that you want to do in 3D static is this software was made in the United States, and you will see that it references hand forces in pounds and locations in inches. Being from Canada or any other part of the world, we will set this to metric units, and you will see that the hand forces now are denoted in newtons and your hand locations in metric units and centimeters. The default humanoid or mannequin that is set for this software is a 50th percentile male human with a height of 157.1 centimeters and a weight of 83.9 kilograms. Based on our class, we do teach for you to design for the 50th percentile female. So the very next thing that you want to do after making this into metric is you're going to want to go into anthropometry, which is under your task input. And we're going to now select female and the 50th percentile and hit apply. You will note that the 3D mannequin down on the bottom left-hand screen is now a representative female of that size. You can also, if you wanted to, for any other different analyses, you can change this again to either gender and different sizes. In fact, it has 95th percentile, so the very large individual, to the very small individual, or you can simply click on data entry and add in any value you want, and the mannequin will represent that gender at that size. For now, we're going to keep it at the 50th percentile. Apply and OK. Now that we have our mannequin in the gender and size that we want, and you can again reference that through this summary window, which tells us the anthropometry or the size of our individual as well as gender, and make sure that we have what we definitely want in our analyses. As previously mentioned, any type of manipulation, manual manipulation of the mannequin down here is done through the top 3 windows up here. So really use these views, top, front, or side, to help you maneuver or manipulate, manually manipulate the mannequin in 3 dimensions. So for instance, if you wanted to move the right hand, and you can see as I hover over the cursor over this circle, which is represented as the hand segment, as I keep my hand on the left mouse button, I can move this arm any which way I choose, which is being rotated at both the elbow and in all 3 axes at the shoulder. And you will see that the mannequin, as I move down in the bottom left-hand corner, moves with respect to what I'm doing in the 3-dimensional, or pardon me, in the stick figure up in the top right. Now, This allows you to move the mannequin pretty much in front to back or fore and aft position. And for more finite control, you can look at the different views. For instance, if you want to move the right hand again laterally, you may want to choose the front view such that the mannequin, again down here in your left hand, bottom left hand view, can move in more control in the lateral if you use that specific plane. And the same goes for if you wanted to move the hand, again, left or right or up or down or whatnot, really left, right in the top view down, and the frontal view will also help you if you wanted to move in the up and down direction. So again, you'll choose where to manipulate the actual mannequin, depending upon the finite control that you need to manipulate the actual mannequin in its specific locations. I also want to just make you aware of some of the controls of when you're using the actual stick figures to move and manipulate the mannequin. You can really mostly only control the joints and thus the segments of the areas that have the dots that are filled in. Okay, open dots usually mean that you can't move that segment unless you move a subsequent segment within the link of the entire link of segments. So again, if you try to move some open or try to manipulate based on some of the open circles, this will not work. Really only working and controlling the full blue closed circles. The other thing is if you want to look at the different views associated with this mannequin down here, the three-dimensional mannequin, you'll have to hold the control button down while you left click, and you can spin that person around or that mannequin around so that you can make sure that you are in the proper position to see what you're trying to manipulate. If you hold the shift key while using the right click button, this is the zoom feature, so you can move around and zoom into that or zoom out of that view by using either the shift button again for zooming and the control button with the left click button, pardon me, to spin this person around. Now, two ways to actually manipulate the mannequin. As I've shown before, you can actually take the closed blue dots and move, for instance, we're moving the hand around right now to manipulate the mannequin. The other way to manipulate the mannequin is use a function within the software under task inputs known as posture prediction. A lot of research has gone into this work to predict the whole body posture based on where the hands, both the left and right hands, are located in space, in three-dimensional space. In the horizontal, so away from the midline of the body, vertical, from the ground up to the hand, and laterally, the left and right from the sternum or mid-center of the actual body. So in your analyses, you could go out to either the plant floor or in your laboratories and measure where your hands would be located to do that lift, push, pull, or lower, where they are in space relative to the feet. For instance, right now in this situation, the left hand over here is 41.6 centimeters away from the front of the body or the ankles. The right hand is 28.4 centimeters. The vertical is 77 for the left hand from the ground up. The right hand is 72, so obviously the left hand is higher than the right hand. And the left hand is 22 centimeters to the left of the sternum, while in view of looking from first perspective of the mannequin. And the right hand is 17.4 centimeters to the right of the sternum. So if we went out and measured where the left and right hands are, rather than manually manipulate and move these dots all around such the segments move, we can make 6 simple measurements so we know where the hands are located in three-dimensional space away from the ankles. For instance, if we put 43.6 centimeters in to the left hand, and we put 53.1 for the right hand horizontal, lateral being 24.1 and 23.2 for the right hand, and laterally we are 32.4, and that should be positive, so we are reaching over to the right hand side with that left hand. 32.4, and we are reaching far to our right with our right hand at 73.4, and we apply. For instance, if we want to use the posture prediction to change the actual posture, we can put different values in from our measurements from either the plant floor or the laboratory for learning purposes. So if we went out and we measured 40.3 centimeters of where our left hand is in the horizontal, and 39.3 for our right hand, so our left hand is slightly further out in front of us than our right hand, we have 176.3 for our left hand and 151.9 for our right hand. So from the ground, our left hand is higher than our right hand, and laterally, our left hand is 16 and a half centimeters away from our sternum, and the negative always denotes the fact that the hand is to your left. Any positive value for the lateral axes will be noted in positive for right, negative for left is 15.4. And if we simply hit apply, we have now moved the mannequin from those 6 points into the posture that hopefully is representative of what we measured out on the plant floor or in the lab. If it's not perfect, what we can do is click OK, and our hand locations are in the proper placement, but maybe the torso angle or some other part of the body is a little bit off from what we actually measured. Again, this is a prediction, so it may not be exactly the way that we saw or when we took a picture and had a picture to reference. We can simply go into locking modes and lock the legs and the trunk, or lock the legs only, or lock the arms and trunk, because we know the arms were there in the laboratory, but maybe they had a bit different of their foot placement. So we can say okay here, and what's going to happen is now you see all of the upper extremities and their dots no longer are closed such that we could move them because we've locked them in that position. The only thing we can really move is the knee and the ankle segments. So what you see here is that we can move the segment only of the lower body because we've locked the upper arms and the trunk. And that will ensure us that our hand locations, which also denoted right down here as what we input into the posture prediction, and we want to keep them in that position and only move the lower body to help represent what we saw out in either the lab or in the plant floor. Again, we can flex the foot, we can move the ankle around, but don't forget, if we lock this position, the reason why we can only do certain movements with this body, like I can't move this right knee, is because we've locked this the rest of the body, and to perform what we want with the knee would require, let's say, a trunk flexion, but we have told the computer not to allow us to move that. So it's one way to lock positions such that we move the body without moving where our hands would be, because where we measured our hands is exactly where those hands should be in this posture prediction. Okay, so now that we use the posture prediction, we learned a locking mode, okay, so that we can, again, lock our position based on what our measurements were and make some finite controls. Let's simply go back to a normal, let's say, preset posture, which is here if you do a right click on any of the top three graphs, we can do a standing lift. Or in fact, let's go into something else where we go to a stooped lift. Okay, so this is a preset posture just so that I can show you how to use 3D static a little bit more in depth. We're going to take off that locking mode so that we can move the mannequin around, and you can see that what was once locked, which was the trunk and the upper limbs, now we can actually start moving the body. I just want to undo that posture just so that we're sticking with one specific posture. Okay, so now you've got this person into a stooped lift, and we're going to start wanting to do an ergonomic analyses. What you'll see is the default force in the hands is 44.5 newtons in both the left and the right hands, assuming that this was a symmetrical lift, such that the left hand is doing exactly what the right hand is doing in terms of force exertion. As well as, if you look at the hand locations, we see a symmetrical geometric location such that we're saying that this is a symmetrical lift. Well, right now the analysis is occurring, the ergonomic analysis is occurring with 44.5 newtons in the left hand, the right hand, so we're lifting 44.5 newtons, again, in both hands, and this is what the summary of this analysis is showing us right currently, such that there is 2,505 newtons of compression that is occurring based on this posture and having 44.5 newtons in the left and right hand. And down here is a summary of the strength capable values associated with this particular posture and lift, such that 99% of all females, because this is the anthropometry as well as the gender that we're looking at, 99% of all females have the strength of the wrist to complete this task. Comparative down here, we're based on this posture and the amount of force that the hands are exerting, only 77% of the population can actually do this task, which we're still above our 75th percentile capable in terms of our strength, but we're getting close to getting into the yellow zone, which is a problem as we want to accommodate for 75% of all females. Now, again, we've mentioned that the default forces in the hands are 44.5 newtons in each hand, giving us a result. But maybe that's not exactly what we are looking at in terms of the job. Maybe the posture is exactly the same, but maybe now we want to try different hand forces such that we don't exceed the 3,400 newtons of compression and we still maintain 75% of female strength down in our strength capability values. Well, we can try different forces in the hands by going into task input again and going into hand loads. You're going to get another window that pops up, and you can see this is where we can input different forces that is being experienced at the hands in different magnitudes. So again, default is 44.5 in both the left and right hands. Down here, we can either type in values into the left and right, as well as the angle at which the force is being exerted. This is just saying that it's straight up at us. Or we can change this not by typing in, but incrementally changing the values using the positive and negative signs. And right now it's going to change 10 newtons every time I click on the negative or positive. And it can go up to 25 increment, a value of 25 newtons in the increments here. Let's just keep it at 44 for a second. What's very, very important is the effort, okay? So we have a left effort and a right effort, and that's what the effort of the hand is exerting in terms of that force. So you can either do it by angle entry, where we can change this to, let's say, 45. And what that's saying is that the lift would be backwards and up. And we could get a horizontal as well, and we could put 45 in there, and, pardon me, and we would get an effort that was to the left, backwards, and up. Now that's a little bit more advanced for what we're doing right now. Let's get this back to 90, negative 90, so that what that's telling us is that that angle, exerting that amount of load, your effort for the left hand is going upwards. Now, what you'll see over in the skeleton-based pictures, the three up the top, is you see an arrow pointing down. Well, remember, in terms of biomechanics or physics, we're looking at the reaction forces. So every action requires an opposite equal reaction. So our effort is a lift, thus the hands want to go upwards, but we are exerting against the force that's being pulled in the opposite direction down towards the ground. So the demand on the body is related to the effort and also the reaction to the effort. Again, the reaction to our effort is the box wanting to go downwards. Our efforts want to go upwards. So you're going to have to make sure that this arrow is always pointing in the opposite direction of what the effort really is. Again, pointing down for a lift up. If it was a lower, then you can change this so that it is a lower, such that this is a positive value in both hands, and we can apply. And if it's a lower, the effort is going downwards, but the reaction to that effort is going upwards. No different than if we were in this position and we wanted to push forward. We could simply just click on the push forward button, and it's going to change the value for us. Push forward and apply. You can see that we want the effort to push forward, yet the reaction to that effort is backwards, towards our backwards. Again, this is very, very important that you have the effort correctly and that the arrow points in the opposite direction of the effort, because again, the body will demand different things, the demands that you are exerting against will cause different demands on the body. Again, this is for reactions, and the calculations within the software is calculating against the reaction of what you're trying to do. Again, if it's a lift, the effort will be up from the hands, and the reaction to that is downwards, and that's again what we're reacting to when we lift. We're reacting to the fact that gravity wants to pull the box down. Okay, so now that we have that covered, again, very, very important, because your demands on the body and thus the reaction to those demands will have a different effect on the body, and you'll get a different result. For instance, if you're doing a lift and the arrow is actually pointing upwards, you'll have much different calculations and the incorrect calculations to what is reacting on top of the body. So in fact, if you had the arrows point upwards, for instance, and you said that you were lifting, you can see that the demands down here on the compression on the back is much different than the actual value of what it should be, such that the arrow should be pointing down. There's a lot more compression. That makes sense. If you're lifting up against something, right, so that the body wants to move upwards, there'll be more compression because of the muscles of the spine compressing on that joint, as we've talked about in class. Comparative to if you're pushing down, you can see that more of the demand is coming from the fact that your body is just going towards the ground, and you've got more of shoulder muscles and less of the back compression occurring. Okay. Let's make sure that we have lift here, apply, and press OK. So now you've got the summary of the analysis in terms of ergonomic analyses here in your low back compression as well as your strength values. Now, what you'll want to do, as I mentioned, is try different hand loads. So at this point in time, you have not exceeded what we've set out to as 75th percentile capable strength, and we haven't exceeded our compression values. We can try different values. Let's just try 100 newtons in the left hand and 100 in the right hand and hit apply, and you will see that more than double of what we're trying, the efforts that we are doing in the left and right hands will cause different demands on the body, such that where we were close to exceeding the capability values of the hip with only 44 kilogram or 44 newtons in each of the hands, when we put 100 newtons in each of the hands, we are now exceeding our protocol, such that only 55% of the females have the strength to do this job in this posture with this amount of magnitude of load in the hands. Same thing with the knee. Only 59% of the female population have the strength to do so based on this posture and the task that we're doing. Compression hasn't exceeded 3,400 newtons yet, but a simple adjustment to the magnitude, let's say 105 and 105, and apply that, now we're getting closer, and let's say 110 and 110 and apply, we are now exceeding the NIOSH compression limits of 3,400 newtons. So this job would fail not only because of the compression that's occurring at the low back, but also because only a percent of the population have the strength in each of the joints to actually do the job. So changing the magnitudes in the hand, once you have the posture set, gives you an opportunity to try different magnitudes of loads that are in the hands and seeing what the demands on the body are. This will help you in your ergonomic analyses to see basically what the limits are of the body, so that you can either design to that, or you can analyze how much less maybe the job should be comparative to what it currently is at this point in time. So let's just keep 110 newtons in the hands, for instance. We can kind of move this little screen over. Oh, apologize, no, you can't. You have to say apply, okay, and we can actually, now that we have 110 newtons in each of the hands, we can start to do some of our analyses with greater detail than what we have in the summary. So what we want to look at in terms of this course so far is a low back analysis in 3 dimensions. So here is where we get the compression values associated, and you can see that those values are the same. And now we also get shear as well. So in our labs, we were asked to report the magnitude of compression and shear for a given value of magnitude or force exertion in the hands. You can see here there are estimates, and that we really don't talk about that right now in this class, but you can see that this is estimating what the individual muscles within this model are exerting such that the compression is this magnitude. You'll also be going into the strength capabilities right here, which is a greater in-depth analyses of what we see down here. And again, what we have, as we've seen in class, we have a left and right side. We have the required moment. Again, that's the required moment based on this posture and based on the load magnitude of what the moments at each of the joints are required to do to maintain this static posture. It tells you also the muscle effect. It tells you the mean population strength in each one of those joints, its standard deviation, and now the calculation of the percent capable based on what the demand is and what the capacity is. So you can see that in this posture with this magnitude, the flexion extension axes of the torso requires, based on what we have here of this lift, of 201.7 newtons. The negative denotes the direction rather than magnitude associated with this lift. So if it was a flexion axis, you would see this to be a positive moment, but negative moments always denote an extension effort by the muscles, and that's what this is talking about here. 201.7 newton meters is very close to the mean of 225.4 newtons, with a standard deviation of 77.9. With our calculation as seen in the class, using the mean and the standard deviation, we now realize that only 62% of the population can actually do the job. Again, the required moment is very close to what the average population can do, and that's why we would have a strength capability of 62%. Comparative to, let's say, the ulnar radial deviation of the wrist, which the moment is only required at the wrist of 4.1 newtons, the population mean is 7.6 with a standard deviation of 2.4. We are far away from our mean relatively, and thus the strength capability associated with this moment demand and capacity calculates out to 92% of the population having the strength to do so. So far with the tutorial, we've learned how to manipulate the mannequin both manually and using the posture prediction, put loads at different magnitudes into the hands, and determine what the demands have on the body and the capacity, what the capacity of the body has, so that we can make a correct ergonomic decision. So let me quickly go through this again, where this is a posture where the hands are exerting an upwards force. The reaction to that is a downwards force at 110 newtons in each of the hands, where we see that we do exceed the 3,400 newtons of compression of NIOSH, as well as we fall under the strength capability values that we have set at 75% for the torso, hip, knee. Therefore, this job would not be acceptable to be completed based on our policy of 75th percentile capable and 3,400 newtons of compression. We can go back into the hand loads and start changing these values, and you're asked to do this in your lab, change these values to see at what value could be exerted such that we don't exceed the compression and we don't exceed, we don't go under 75% of female population strength. So what we see here is 50 newtons, and then we tried 110, and we now move to 50 newtons in each hand, so a total of 100 newtons. And we applied that in a lift, and what we see is we get a lower compression, 2,583 newtons, but we've also now allowed this job to be done by at least 75% of the female population in all of the joints. The hip being, again, if we increase this by a couple newtons in left hand or right hand, this will fall below what we have set as 75% population. So again, in your lab, you had a couple of tasks to analyze. You are to manipulate the posture to replicate what you saw in the lab. Try different magnitudes of loads in the hands with the proper direction of the effort, don't forget, and tell us what load would be acceptable such that we don't exceed the compression, such that we don't exceed the percent capable, and give us your ergonomic analyses. We've also asked you to try different loads and report back the strength values at each one of those joints as well as the compression. And we're done the tutorial. There's many more things you can do within the software, and you may want to try these things out, but for the lab component, what I've given you is again, direction on how to go about using the software.